to present our work today on empowering WebAssembly within kernel interfaces. So to start off this talk, I want to highlight that we're at a state right now where languages have evolved in expressiveness, their reasoning capabilities, static, dynamic analysis, and likewise, platforms have also evolved. We have more powerful compute, we have heterogeneous compute, and we have the ability to operate more energy efficiently. But what we don't realize is that we also carry a lot of legacy baggage to get here. We have tons of systems today that are deployed that run on legacy platforms and legacy programming languages. And in fact, this problem is only going to get worse because the advancements we have today will become legacy soon in the future. We might have new languages that are more expressive, more heterogeneous platforms that we can't potentially scale to. And legacy software management is actually a huge issue. Today, according to the US government, over $1 trillion is spent just in managing legacy software. And this hampers the growth of numerous companies in the Fortune 500. A big issue with legacy software is maintaining security. Security is a huge threat, but it also produces inefficiency and opportunity cost, which basically inhibits the growth of a company. But simultaneously, while we have these issues with legacy software, computing paradigms are evolving. With the rise of networked systems and the internet, we now have this ability to deploy potentially untrusted code to numerous domains, including web browsers, cloud computing systems, and much more recently, IoT and edge computing systems. With this ability to now deploy untrusted software, there is a problem though. Vulnerabilities are increasingly exploitable. The ability to execute remote code execution attacks is much more prevalent today than ever. And in fact, irrespective of how expert your C programmers are, for example, in OpenSSH, where they claim to have a near flawless implementation, you still have bugs like the regression bug that is exploitable on millions of Linux boxes. And that just is the nature of the language that we're designing with today. And the result of this is that millions of deployed devices actually obliviously end up using vulnerable low-level software. And with these being legacy pieces of software, it's hard for people to actually go in and debug the specific segments that are causing these vulnerabilities to occur. But we have a solution for this. In fact, virtualization has been a really good way of taking software that's potentially unsafe and encapsulating it into a box. And across all of these domains we see, there are numerous ways we can virtualize software. For instance, in web browsers, we've seen language-level virtualization with JavaScript or ActionScript or even NACL. In cloud computing, we've seen more OS-level virtualization with technologies like Docker, LXC containers, but also hypervisor-based solutions like QEMU and Zen and so on. But when we get to edge computing, it gets a little harder because we have a few challenges here. For one, edge computing is quite a heterogeneous platform space. We have to operate across a diverse number of ISAs and platforms, but we're also resource limited. We run on potentially low memory, low compute embedded devices, and we need to be able to scale to these targets. And finally, a lot of IoT and edge systems actually have software that's designed and deployed by third-party vendors, which means we can't rely on a specific programming paradigm or language when designing software that targets these systems. But one virtualization technique actually that has been very promising across all of these domains has been WebAssembly. So to give people a bit of a primer on WebAssembly, it's essentially a bytecode format, but what makes it slightly unique is the fact that it's a polyglot compilation target, which means we can actually target numerous compiled and interpreted languages, potentially memory unsafe, like C and C++, but move them to this safe, type safe, and memory safe sandbox. And sort of the really nice property of WASM is that we have structured control flow integrity in WASM, along with a non-addressable execution state, which actually means that RCE attacks are impossible by design, just by porting to WASM. And finally, with WebAssembly, one of the really nice properties we see is this idea of flexible system interfaces, which allows us to embed WebAssembly code into numerous host environments. So for example, in the browser, we have the JavaScript API, which lets us interact with JavaScript and the browser system. But we can also design custom system interfaces to interact with cloud and edge systems, for instance, as we'll get to later in this talk. So just to walk through a typical edge deployment scenario that we might see today. Right now, we have technologies like containers. These take anywhere from megabytes of RAM and even up to a gigabyte of disk. In fact, I think the Python binary for Docker has about 600 to 700 megabytes, which is huge, and also a high startup time. But the other hidden point here is that we are actually limited to the ISA. And if you want to deploy this to numerous ISAs, what you essentially have is multiple containers in a trench code, which means you have a Python binary that's multi-arc is now n times the size that it would be for a single architecture. Additionally, you can't really deploy these to small devices like embedded devices that only have kilobytes of RAM. In contrast, with a technology like WebAssembly, what we can do is run with runtimes that are potentially in the kilobytes of RAM, and in fact, use also kilobytes of disk space. They have a really quick startup time, and they can actually scale to these devices that have very constrained memory requirements. But all this is good. We've tackled these problems of heterogeneity, resource limited, and language diversity. But WASM ecosystems still have not become pervasive. So in the web, we've seen this take off a lot. In the cloud computing, it's sort of a maybe. People have started integrating WASM as a replacement to containers. But in edge computing ecosystems, it's pretty much a no-go. And we believe the major obstacle for this is the porting friction to system interfaces. So currently, the major system interface that exists for WebAssembly is this system interface called WASI, which is essentially a new API with this new capability-based security model. So their primary goal is to basically enable security in the cloud. But there are a couple of snags with actually using WASI. For one, it has a very minimal feature set. It doesn't support numerous OS-level features that we would expect, like threads, memory mapping, processes, and even signals. And in fact, one of the main goals of WASI is to be divergent from POSIX, which means that programs that are written against standards like POSIX will never potentially compile against WASM with WASI as a system interface. In addition, WASI is an evolving specification, which doesn't make it very useful for long-term deployments. They have backward compatibility changes that often break, so we can't really trust this when we want to deploy something for 5, 10 years. Finally, despite the minimal feature set of WASI, it's actually incredibly complex. Like currently, the implementation of WASI for just these features is over 10,000 lines of code, and it's very likely to increase by 5 or 10x with new releases of WASI that we're anticipating in the next 4 to 5 years. And what they actually do is re-implement this implementation across various engines. So there's divergent, buggy re-implementations across these where they don't actually agree on the semantics of specific calls. So while WASI is really good from an application perspective in terms of providing this security model, it doesn't really make sense from a system interface level of what you need on the lowest level of your privileged engine. So our approach is actually to take a bottom-up interface design philosophy. So our philosophy is that WASM engines should ideally operate like virtual CPUs. WASM is an ISA. It's not a hardware ISA, but it's a software-defined ISA. Why can't we provide an interface that looks very much like a CPU? And in that line, what we actually do is expose OS syscalls pretty much directly, but safely to WASM. So this insight actually has several implications. One is that we can actually port applications that were designed against traditional OS APIs to now run over WASM. And this is pretty much the entire space of applications. So many applications have been designed against traditional stable OS syscall interfaces. Now, most people think when I propose a solution like this that we're actually defeating the purpose of security because, hey, we're letting our application access all these syscalls, which are potentially unsafe. But what we actually argue is that we increase security because now what we do is we can layer high-level APIs over kernel interfaces. So now that WASI library that's divergent and buggy can sit as WASM code over the engine. So what this does is actually reduce our TCP and allows for standard and portable implementations across numerous WASM engines. In fact, the implementation of kernel interfaces in our experience is under 2,000 to 3,000 lines of code. And we can use this to virtualize essentially any high-level API, which is nice. And finally, WASM is this polyglot compilation target. We really want it to be targetable from a number of languages. With an OS syscall interface, we're actually able to seamlessly target languages that were originally designed to target these interfaces. And so the way we realize this is with a generalizable recipe that we see applicable to numerous OSs, but we demonstrate a proof of concept for Linux and Zephyr in our paper. So the first part of this talk is mostly going to focus on Wally, which is the Linux interface that we designed. And to kind of scope out the effort, we needed two things, which is to determine what was the critical mass of syscalls and how would we actually make this portable across different platforms. And so the interesting thing here is that most apps actually use a subset of under 130 syscalls, and these operate very similarly across ISAs. So this is really nice, and actually this has been studied a lot in literature in ASP+ and EUROSYS. People have found out that only a small number of syscalls contribute to high API importance in the Linux ecosystem. And so with that, we started our prototype on Wally with a current range of support of 142 syscalls spanning 3 architectures, x86, ARM, and RISC-V. And so there were a number of subtle design decisions that went behind virtualization for Wally. These 6 elements in particular listed on the slide. I will defer the specific details of each of these components to the paper, which I encourage everyone to read. But at a high level, the main goal of Wally was to enable zero-copy pass-through syscalls to support asynchronous signals with safe points, to support processes much like you would in Linux with the one-to-one process mapping, and command line arguments and environment variables like one would expect in a typical deployment. But we also coupled this with ISA portability across the ISAs I just mentioned. And we try to approach security with a minimal check kind of policy, which is that we just want to preserve WASM guarantees. We don't really want to impose further security policies because we believe those should be layered over your kernel interface. In particular, what we do restrict, though, is non-local go-tos like long jump. These will eventually be supported by WASM exception handling. We also don't support unsafe file system endpoints like proc_self, which is a known sandbox escape. And the nice thing with this is these 6 components are actually pretty generalizable across different OSs. And we demonstrate this by creating one for Zephyr, where we deploy to this kind of tiny nuclear board that's an embedded microcontroller with only 300 kilobytes of RAM. And we were able to run Lua binaries virtualized under WASM under these memory constraints, which is really nice. And so really the big takeaway with this talk that I want everyone to get is that you can actually port applications completely unmodified to run over WASM now. You can almost think of it as a universal binary format available to you today. We support numerous standard libraries for C, numerous language runtimes, including Rust and Bash, Lua, and many more. To demonstrate that we can actually virtualize and layer high-level APIs, we take a common implementation of WASI called libuvwasi and pass the entire test suite pretty transparently, which is nice. And something that most people really don't realize the benefit of is this ability to plug into build systems effortlessly. Oftentimes, people spend a huge amount of effort mangling build systems just to get something to port. With Wally, it's incredibly easy. All you do is replace the compiler toolchain, and things just work. In fact, there are a lot of places where we had to generate intermediate binaries for our build system that get executed. And these intermediate binaries actually execute transparently as Wally binaries, and we didn't even know until we went and looked back at the logs, which was extremely insightful, I think, to the range of applications we could apply to. And in fact, we have deployed this on an edge cluster we have at CMU. This is an edge cluster consisting of over 20 devices, ranging in performance from high-power x86 to really low-power ARM and RISC-V devices. In fact, we have even weird ISAs and CPUs, like we have this Intel compute stick that's like probably ancient and no one uses, and we're able to deploy Wally to run on these legacy hardware. And we actually have a follow-up work that's going to be presented at UPSLA this year on how we use dynamic analysis coupled with Wally to enable, new research over this framework. So Wally itself has a very low intrinsic overhead because what we mostly do is end up having stateless zero-copy syscalls. And this ends up being basically less than 10 lines of code and uses very little memory. And details of the overheads are also available in the paper. But using Wally, as opposed to the intrinsic overhead, also has this extrinsic overhead, which is like, what is the overhead of using WASM virtualization itself? Because this matters for people who want to, consider WASM over something like containers. And so what we see as of today is that the memory of WASM is much more efficient than containers, which has been, I think, well studied across literature. But for sake of completeness, we like to include it here as well. But in addition to that, what we also have is that we have an extremely fast startup time. Containers typically take the order of hundreds of milliseconds to start up. With WASM, it's pretty much instantaneous, like most emulator technologies. But we have a runtime that's much faster than emulator technologies. So WASM still does, if you notice this graph, lag behind containers. Containers are still in runtime faster than WASM. And this is primarily because compilers are still sort of in their early stages. WASM is a pretty new technology. And there's no reason that we see why compilers for WASM will not improve to eventually become near native performance. And so we anticipate this will happen in the next maybe 5 to 6 years. So with WASM kernel interfaces, we actually unlock numerous opportunities, and we hope this will be useful across PL researchers who are working on WASM and OS researchers who are working on low-level systems. In particular, for edge systems, we have this way of now modularizing and accelerating WASM APIs. And this is really useful in edge systems because you want to be able to move your compute across different devices. Finally, we also have this way of taking OS distributions and maybe potentially running them secure and sandboxed across different ISAs. And this is really interesting because we have in-progress work where we're trying to take Alpine, basically compile its entire package distribution to run over Wally. We can also place syscall interposition policies to run over WASM engines, which can now be sandboxed and get the benefits of WASM portability and CFI. And finally, WASM can provide this really nice full stack substrate for verification, where potentially all the security research that goes into WASM will allow us to push verification up the chain and kind of reach the pie in the sky for full stack verification. And so with that, I would like to conclude my talk. The Wally ecosystem is actively expanding, and we highly welcome collaboration. We have toolchain support in Rust that is currently being upstreamed, and it's actually been merged into mainline, the first pull request, which is really exciting. And we have engine support in Whammer, but we also have upcoming engine support in 3 other engines. And I've put up my email there, and I'm happy to take questions. Thank you.